All right, welcome to the webinar. So today I'm going to talk about the evolutionary approach to microservices and focusing on the position of the different products, if you will, that have been released under the Axon flag. Of course, Axon Framework being the best known in that stack. But we have Axon Hub and Axon DB as well. We've noticed that well, we get a lot of questions around, okay, how does that work? How can we implement that vision that you have? So I want to start with that vision that we have on how software should be built to be able to evolve that software into microservices. Now, traditionally, we see a very common architectural style, and this stems from the 70s. I can trace it back to the 70s. But the layered architecture has been a very popular architectural style, and many applications that we still build use that architecture. And while there's nothing per definition wrong or per se wrong with this architectural style, the demands that we have on software are not really fit for it. So typically what would happen in an layered architecture is you have a domain model, and it could be anemic. It often is, unfortunately, but it could also be a rich domain model. And on top of that domain model, we build services. And you'll notice that a lot of these services map really nicely to one of the entities or concepts in the model, making access for this service layer to the model really straightforward and easy to understand. Unfortunately, especially when applications grow more complex, you tend to get services that need to know a bit about everything. So the model doesn't really offer them one place where that service can get the information it requires or offers the behavior it requires. So such a service in the business layer or in the application layer, whatever you want to call it, will need to access a lot of entities, and as a result, we get these humongous SQL queries. I've unfortunately seen too many of those queries in different projects that I've been involved with in the past. Now, this particular query is not extremely readable. It was donated to me, so I could use it in presentations like these. So fortunately, I didn't have to go through the process of writing it, and I'm even happier that I don't have to go through the process of maintaining it. But here's a little summary. This query contains 22 joins and 6 subqueries. Now, if it's your job to maintain this query, I wish you all the best of luck. But unfortunately, this query is just proof that the domain model that is underneath the application is not suited for the behavior we expect from the service layer. And this is a very common problem. And how do we solve this? Well, any problem can be solved either by adding more technology or adding layers of abstraction, whichever is your preference. But often in applications, what you see is that developers have looked at technology as the solution to a lot of the problems they have. And if performance is your problem, a cache is the solution, or a lot of caches. So this is a bit of an exaggerated example, obviously. Worker pools to do stuff asynchronously is not going to make things easier, and I seriously doubt if it will make things faster as well. And if you ask a team that has been building software like this, what that software looks like, you often get an explanation of something that's really fast, right? We need the performance, so we have caches all over the place. Unfortunately, what they ended up building is slightly different. It has all the characteristic and maybe outer looks and feels of something that performs, but really when you get into it and start driving, well, I'm pretty sure it's not as fast. So in software, actually what we have built is, there's a name for it, and it's called the big ball of mud. And I've used this picture in a lot of presentations, and I like it because it shows the big ball of mud is not made of mud first. So it explains where the concept of a code smell comes from. But this picture also includes the architect that is proud of its creation. But definitely as a developer, you won't be very happy working on this big ball of mud, I'm pretty sure. And this is where Axon really originated, right? In being Axon Framework was a project that started about 9 years ago to tackle this complexity problem and have a different approach. And the way Axon wants to do that is by introducing command query responsibility segregation, or CQRS in short, which is a very simple architectural style where you split the command side of an application from the query side. So one part of the application is responsible for handling changes to your application, while other components are responsible for providing information about the current state of this application, which allows us to create different domain models, different models for the same domain concepts. And in some applications they look alike, and in some applications they're completely different. Them being alike is not a bad thing, because generally you'll see that the non-functional characteristics of these different models, they differ a lot. And in this example, obviously we need some way to synchronize, and nowadays events are a very popular means to do that. But the differences are quite often non-functional. So you could have certain components that have very high performance requirements. In this example, I just mentioned 1 million transactions per second with relatively low latency, where other components might have less strict performance requirements. And the type of effort you want to put in these components is completely different. Now, if you have one domain model to do everything, it's very hard to make this differentiation in different parts of your model. And right now, we can do the optimizations very locally for every part of our model. Now, as I said, this started around 9 years ago, and around the end of 2009. We started writing our first code for the framework. It was really experimental at the time, and just finding out if this would be an approach that really helps building software that doesn't turn into the inevitable, quote unquote, big ball of mud. Our first production user reported itself early 2010. That was something completely unexpected, because it was absolutely not production ready at the time, was our belief. The company was a company based in France that started using it, and they said they had thoroughly tested it, and they had the full belief that it would work, and it did work for them, obviously at the time. And that gave me the confidence, me and my colleagues, the confidence to start using it in our own projects as well. So most of the frameworks start the other way around. You start using it yourself first, but in this case, we had our French friends to run it for us first. The 1.0 release only came after that. Of course, a 1.0 has to be production proven, or at least proven to be production grade. And generally that means it has been in production for a while. A few years later, we noticed that we needed to improve on the APIs, and we of course have, after a couple of years of using CQRS, you learn a lot of things. So we had the 2.0 release, and again, a few years later, we had the 3.0 release. At the moment, we are at 3.3 of Axon Framework. Now, in 2017, so a little over a year ago, we founded AxonIQ, and at AxonIQ we launched AxonDB early this year, and Axon Hub a couple of months later. Of course, AxonDB and Axon Hub were not started from scratch by AxonIQ. They were concepts that had been evolving before then, and some ideas have been were formed, which allowed us to do a seemingly quick launch of these products after founding the company. Now, in the meantime, what we noticed is that Axon adoption really rapidly increased. And I would really love to say that this was completely because of the 3.0 release, because it's around that time that the increase started. Unfortunately, we don't believe that's the actual case. There's probably some features in Axon 3.0 that made it easier to use and easier to get started that helped adoption. But there was something else happening in around 2015, 2016 that had a major influence on Axon adoption. And that's microservices. Microservices are still becoming increasingly popular, although we might be at a position where people start thinking, oh, is microservices really the silver bullet? Well, guess what? It's not. But there is a lot of there's a lot of added value of microservices, of course, at a cost. And that's really where Axon comes in. So the idea of microservices is to take a system and split it in smaller components, which are more manageable. And the core drivers for doing that are the promises of agility and scalability, right? We can scale different components differently, but we can also modify components and change the behavior of the system by just changing a couple of services in there, right? It helps scalability also in the sense of team size, right? It's easier for a team of 200 people to work on 20 different products than it is to work on a single product altogether. And the use of Axon in microservices environments have taught us something really important, and that is about the monolith. Now, there's a lot of discussion about a monolith and are they good, are they bad? And I think that's because a monolith is often confused by a big ball of mud. But I want to be really clear, it's not the same thing. It's very much different. For one, the monolith doesn't smell. But secondly, I think it's easier to break a monolith apart than a big ball of mud. There's no fun in breaking a big ball of mud apart because you don't really know where it's going to break. And it's the same for applications. If an application doesn't have a seemingly any structure, any obvious structure, it's really difficult to take components apart because you don't know what you're going to break. And of course, there's a lot of discussion about, well, should you build monoliths or should you build microservices? And there's an interesting observation by Martin Fowler that almost all the successful microservices stories started with a monolith that got too big and was broken up. Unfortunately, there's also some stories where breaking a monolith was not successful. So that's why it's almost all. The other case is also true. Almost all cases where Martin Fowler has heard of a system that was built as a microservices system from scratch has ended up in serious trouble. And you could, of course, wonder why. Why is it? Why do systems that start as a microservices system? Why are they so? Why is it so probable that they fail? And that's because microservices are really hard. There's a lot of stuff that you need to take into account. And it's, of course, it's the technical stuff, right? Dealing with errors and transactions are completely different in distributed systems, but there's something else. And that is much more of a problem than technology, right? We can't solve all the problems by adding technology. And it's about where do you split? What makes up the boundary of a service? What goes into one service and what goes into another service? And what we see being used in practice is definitely not a good approach. And a friend of mine called this noun-driven design. And he said, that is basically what you see in most microservices designs. And it's a very simple algorithm. And this is a negative thing, right? So don't do this. If you're taking notes, make sure do not do this at home or at work. But if you see a noun, that's a service, right? And this is what happens a lot in practice. If you look at Stack Overflow about most of the questions asked there, you get things like, oh, I have an order service and I have a customer service and now I have this thing and I don't know where to put it. Or you get the product service and an inventory service and everything. And instead of building a monolith which turns into a big ball of mud, now you have built a distributed big balls of mud system. You end up with a, well, some people call it a distributed monolith, or I don't think that's right because of the smell involved. But you get a system that is completely non-maintainable. You'll have to do lockstep deployments of a lot of services to be able to add features in production. And once you require other services to go live before you can deploy, it's a sign of not having a proper microservices system, but having a distributed big ball of mud. So the approach we suggest is slightly different. So let's imagine you have an idea for a business case, right? And it could be that you have software already and you just want to change the way you're building it. That's fine as well. And you think microservices is a good destination to be for providing this service that you have in mind. Now, of course, you can take the short route, but then you end up with a microservices first approach, which is really dangerous, right? We've seen the observations by Martin Fowler, and this is a very dangerous path, and you'll probably lose track of where you're going. You're not ending up where you believe you would be, and you end up with this distributed big ball of mud. So you want to take a slightly different approach. You want to build probably a monolith first, but you want that monolith to be structured. And CQRS has given us the handles to do that, right? So you can build different relatively isolated components to in your monolith, but still deploy them as one. That is very convenient and very simple, and you can learn about where these boundaries are, what makes sense to deploy together, what kind of processes are used together and which ones are not used in combination with that specific component. And as you learn that, you can decide to extract certain components and start deploying them separately from the rest of the application. So in this example, the blue component has been deployed separately. Now, quite often, this is driven by non-functional requirements. There are some non-functional aspects in our system or in our company that forces us to, or that drives us to deploy this separately. And it could be things like team size, it could be life cycle of the application, maybe the blue component changes very rapidly or less frequently or more frequently than the other components. Maybe it has a stability problem, it has different performance requirements, etc. It could be a lot of things. But any of these things could be arguments to start deploying it separately. And as time progresses, we can extract more components and we can even scale them out if we want to, or scale out slightly different versions to do A/B testing and all that stuff. And while we are doing that, why can't we stop bothering about how many instances we're running of things altogether and go to a serverless world where we say we just deploy our components and have a platform run it. And this is also AxonIQ's dream destination, if you will, for software. Now, the driver in making this possible is what we call location transparency. It's the communication between components should be such that the components are not aware of the location of the component they're communicating with. Right? It should not make any assumptions on the other location. And in a lot of traditional microservices, everything is distributed basically by design. So if you have an HTTP protocol between two components, you're not location transparent anymore. Maybe you don't know the physical location or IP address or something like that of a machine, but you are accessing a URL. So you know that there's a certain service that has an endpoint, and you know that service is not you because you're accessing it via HTTP. But what if you want to split that service and start splitting the behavior into two? Then all your clients need to adapt as well. So that's not location transparent at all. So what you see in practice a lot to achieve this location transparency is using events, right? So event-driven microservices have been very popular because you can send an event and you don't care about the destination of an event, and it will be handled somewhere at some point in time. And as a sender, you really do not care where that happens. So systems like that, they could look like this. You have an order service because noun-driven design is unfortunately a big driver in microservices design. And you have another service that needs to know about items that have been ordered, right? For financial reasons, to send invoices, doesn't matter. They just need to know, maybe analytics. And of course, every service has its own database, right? It stores its own data. It owns a certain amount of data that it captures in its own database. And there's a line of communication between these services. Now imagine the order service emits a number of events, some events that occur in processing orders, things like order created, item added, item removed, and order confirmed. Now, you could think that the service on the right just needs to listen to item added events because those are items that have been ordered. Well, they're not. These are items that are supposed to be ordered, but we need an order confirmed first. So there's a bit of mathematics going on. And of course, this is very simple mathematics for the sake of the presentation. But in practice, this math can become pretty intricate and elaborate as well, which is problematic because we're basically copying behavior, right? An item is ordered if it was part of an order that was confirmed. So if it was added, not removed, and part of an order that was confirmed, then it's an ordered item. So we have logic here that's being copied from the order service to the other services. But things get worse. I've seen examples of how beautiful event-driven systems can be because it allows you to have non-blocking, location transparency, and achieve great performance, unfortunately at a massive cost of complexity. So imagine the same order service, and now we have a payment service and a shipping service that need to work together somehow. And the other order systems emits an order created event, right? It could be order confirmed, it doesn't matter. An order is placed into the system. Now the shipping service picks that event up and emits an inventory confirmed, right? So shipping has confirmed, yes, we have all the items, so we're okay. We're okay with this order. But the order service waits for that confirmation. And now it says, hey, I'm ready for payment. And there's an intricate coupling going on here because now the order service is aware of the shipping process, right? So the order service needs to wait for shipping to basically confirm the order. And now the ready for payment event is sent, but of course we say it's ready for payment. So we're really targeting the payment service, right? We're emitting an event with the intent to send it to a specific service, which is an anti-pattern for events. And then when the order is paid, then the order service says, okay, now I'm ready for shipping. And now it's shipped. So the process here is very similar to a process that we would have with, let's say, a direct point-to-point communication, except that we have inverted all the dependencies. So the things that events do is, instead of having a dependency of the sender to the receiver, now we have a dependency from the receiver to the sender. So we're just turning dependencies around, but they're still there, and they're less visible, right? The problem with events is that you cannot really track them with your finger. You just see emit event, but you don't see where it's being handled. And the basis of this, the basis of the problem here is that there is more than one reason for a service to send a message. And in most systems, events get a lot of attention, but we forget about the other reasons. And those reasons are commands. You want to know, you want the system to do something, right? You want the system to make a change to its state, so to say. Or you want to do a query because you're interested in knowing something about the current state of the system. And using these explicit messages is a very powerful means to achieve this location transparency. And we'll get to that in a second. So let's have a short look at the differences between these different types of messages. So commands are generally routed to a single node, right? You have the intent to change something. That intent needs to be fulfilled by some components, so it's routed to a single destination. Preferably the sender should not, at least in the logic of the application, should not be aware which destination that is. That should be dynamic. If there are multiple candidates, we should use consistent hashing to make sure that commands that target the same entity or the same concept are routed to the same machine. So different items being added to the same order should be handled preferably by the same instance of a service, so that that service can optimize its processes by caching, for example, and not like caching the way we did it in the beginning of this presentation, but really caching as an optimization of something that works very well without it. So those are commands. Commands typically also provide feedback. So as a sender, you get some acknowledgement or some feedback about whether your command has been handled, was found to be valid or not, right? Now the other one is events, and events are typically pub sub. So every component that is interested in that event can handle it. There's no feedback, so senders don't have to wait for anything. They just publish the event and forget about it. They just move on with their lives. Now, quite often consumers have specific expectations on ordering of events. And there's a lot of discussion about ordering of messages, and you cannot guarantee. Well, that's not completely true. There is specific things that you can guarantee. There are certain aspects that you cannot, but a consumer can express certain ordering requirements. Some systems out there allow you to provide ordering requirements, but only as a sender. But what does the sender know about the recipients of the events? Well, nothing. So we believe it should be in the consumer of the events to decide how ordering should be guaranteed. And this results in multi-threading, for example. How do you distribute events? Which events are processed by what thread if you do multi-threading? If you require full ordering of everything, then you can basically only have one thread. You must execute everything sequentially in the order events arrive. And the last one are queries. And queries in Axon Framework are a relatively new member, so to say. And queries follow different patterns for different use cases. Typically, you'll have point-to-point queries. So you have a question, a component can answer that question, and basically you can use consistent hashing if you like, but you can also use a round-robin load balancing. In some of our Axon products, we allow load balancing based on the performance of the recipient of the query, things like that. That's very useful if you have a single true authoritative answer to your question, right? But sometimes you have a query where different components might have a different opinion. In that case, you could do scatter-gather queries, saying I'm going to send a query, and every component that believes it has an answer to my query can provide it. I'm going to wait a certain amount of time for those answers and do a reduce to reduce them to a single response that I'm going to use onwards. And the last one is the subscription query, which is basically a question that starts with, can you keep me up to date on? So you stay up to date on the state of a certain certain component, and the more we well, the longer that we have the support for this subscription query, the more use cases we see of it as a very powerful means to reduce complexity in a lot of components and simplify communication between components even more. And at last, I want to emphasize that an event and a message is not the same thing. So seeing every message as an event is not going to help you, right? It's just about inverting the dependency, but not really reducing coupling between components. So really, we use event. Event is a type of message, but it's just one of three types of messages that we see out there. And if we look at how Axon deals with that, if we have this this architecture, an architecture like this, where we see the command handling component on the top, the query handling component in the bottom, and the event handling components, basically reading events, consuming these events, and updating the query models. In Axon, we use the buses to decouple these components. So the UI in this case communicates with these command handling components by putting command messages on a command bus. Now the sender doesn't know where the recipient is, where the actual handler. It might be in the same VM, it might be somewhere else. It doesn't care, right? The same for the events. The events are published on an event bus in Axon, and queries are, well, you can guess by now, are put on a query bus. And these buses are a perfect location are a perfect way to provide or to achieve this location transparency. So the location transparency boundaries are really around these components that communicate through commands, events, and queries. But there's another thing about events. They retain value. There's the fact that an event occurs or has occurred just doesn't just have value at the moment it occurred, but it contains very valuable information that might be valuable even 5 years from now, or in some cases even longer than that. It might also be gone in a couple of seconds. That really depends, of course, on your environment. But generally, they retain value much longer than a query. Once the component that asked the question has its answer, well, it has what it got, and it's got what it needed, and it can move on. But there's some value in keeping those events and in storing them. So Axon Framework supports event sourcing, which is an architectural pattern where events are really considered the source of truth, right? So components rebuild their internal states based off of these events. And what you need for that is an event store, right? You need a place to store all these events. And there's something really special about this event store that is different from a regular data store or database, if you will. And that's because the use cases of an event store are very specific to it, right? So let's have a look at what event sourcing, how that works. So let's say we have some order processing service, and it emits events, and some other component is using events, right? Now this, in some descriptions out on the web, I see this described as event sourcing, which unfortunately is a bit misleading because it's not the full story. At least it becomes event sourcing when the order processing service itself uses those events as the source of truth, basically meaning it doesn't need a database anymore to store its current state, right? its state is defined by the events it has produced. So events are not a side effect, they are the source of the change. And that is a very important aspect of event sourcing, and this gives you the reliable audit trail, right? Nothing can have happened unless you have an event in your log. And when you do this cycle back, that's when you have event sourcing. So right now, if you want to do something on an order, you need to know the current state of that order to validate an incoming command. You replay the events related to that order and find out what the current state is. So you can only confirm an order unless you can only confirm it if it has not been confirmed or canceled previously, right? Validation like that. So that's how event sourcing works. And if you look at the operations that an event store needs to be able to do to support that, obviously the append is the most important one. And in that append, it needs to validate the sequence. So it needs to be able to ensure that nothing else happened that might be in conflict with what you are currently describing as a new event. And some of the systems described out there being used for event sourcing are not able to validate that sequence. And I think that it's probably solvable by, as I said before, adding more technology, and but that's not going to help keep it simple. So we need to append. We don't need update. We don't need delete. We only append new events, right? We never have to change an existing event. Whatever happened has happened. Right? Now another one is a full sequential read. So once all these events are added, there's probably other components that are consuming these events, and they want to be able to track whatever is being processed. So they do a full sequential read of all the events that occurred in the past. But another one often overlooked is that you need to be able to read the event of a single aggregate. So aggregate is a DDD concept, domain-driven design concept, and basically it's your logical unit of consistency in an application, and whatever that, you need to be able to reconstruct the state of that aggregate based on the events that it emitted in the past. So you need to be able to quickly find events that were emitted by a specific aggregate instance in the past to reconstruct its current state. So those are the operations. Now, this is all nice and it will work if you build one or two applications, and the whole process is probably relatively simple and straightforward. But at scale, we have different rules. Everything as simple as small scale, at large scale is different. So how does this work when you have a lot of components to route events and commands and queries to? How do you scale that? Well, fortunately, the answer is simple, but unfortunately, the answer is you don't. You can't naively take this concept and just introduce it at an extremely large scale. And it's not a technical reason, again, right? The problems are not in technology, so let's not try to find the solution in technology. But what you end up with is an unmanageable mess. You'll have components, for example, that want to know when an order is placed. So when is an order placed? Well, it's not that simple, right? There's an order component, but it doesn't talk about order placed events. It talks about orders are created, items are added, shipping address added, and then it's confirmed. Well, maybe it's confirmed is the term we mean, but probably the shipping module has different expectations of the information inside an order placed event. So really what it needs to do now is listen to all the events by the order system and do that mathematics again. And we talked about this earlier. This is not a good design. It will introduce a tremendous amount of coupling between the shipping module and the order module. And in DDD, there's a concept of a bounded context that we can use. And within a bounded context, components share a language. They share the understanding of what a specific word means and what attributes are important in that concept. Outside of the bounded context, components will have a different understanding, and there's probably a translation required to make these communicate. So our recommendation is, within a context, it is safe to share because you speak the same language, so you can share all the events and components can listen to these events and do whatever they want with those. But in between these contexts, we want to be more conscious about the events that we share, and we want to speak a different language, maybe not as detailed as the one we speak inside our bounded context. So again, if we have our shipping module here, which wants to know when an order is placed, and we have the order module over there, we probably need a component in between, and you can see that as the little purple ball that does a translation, and this is just a component listening to events, and it might listen for the order confirmed event, and if that occurs, it does a query to get some order details and sends out a more coarse-grained order placed event. And this order placed event is useful outside of the order bounded context in case any component wants to know about this, the state of an order. Sometimes these events are considered milestone events, right? An order confirmed is a very important step in a process, and really a milestone has been achieved. And generally, you'll find that these milestone events are good triggers to start notifying other contexts that something happened. So if we have this story of evolution, how does Axon Framework and how does Axon DB and Axon Hub, how do they fit in this in this story? What's their place? Basically, if we look at our structured monolith, you'll find Axon Framework in the middle, doing the coordination and messaging of all the components in between, but also managing instances of our models and taking care of a lot of the non-functionals that we have when using messaging. But basically everything happens inside a JVM, and we can use things like the simple event bus and simple command bus, and it's generally a smooth, simple ride from here. But things start changing when we have more than one component, for example, because we split out a component. Now we have two components, and still we have Axon Framework inside of these each of these instances. But we need some form of communication between the two, and probably including storage, because events are generally not just passed from sender to recipient, but they're stored somewhere so that the recipient can receive those messages at its own pace. And this is where Axon DB and Axon Hub come in. Together they can play the role of the component that takes care of the messaging between different instances where Axon is deployed. And this is, I would say, these are very important components inside such an architecture, because they give you the location transparency and allow you, for example, to extract more components seamlessly, right? We can extract another component, start deploying it separately. It will connect to Axon Hub. Now imagine that the component on the left was communicating with a component on the top right. If we did that traditionally with HTTP, probably we'd need to change endpoints now, either for that component on the top or for the component on the bottom, because they're not the same service anymore. They're different services. But we're not. We're using, well, in this example, Axon Hub. So all we do is send a query, and Axon Hub knows, oh, that query can be handled by the component on the top right. So I'm going to forward it there. The sender doesn't even know where these components go, right? So we can very simply evolve our application and start splitting components without other components being affected by that split. And if we need to scale that component on the left, we can do that seamlessly as well. We can just start deploying multiple instances, and Axon Hub and DB together will coordinate activities such that other components will be able to use the fact that there's now more 4 instances of the component on the left. So in this architecture, the Axon Hub is really the component that provides us with this location transparency and elastic scalability features for our environments. It's very zero-config, right? You just need to start it, and it will it will use the information that is provided by the applications when they connect to Hub for the routing, and of course it assumes the routing patterns required for commands, queries, and events, which are very safe assumptions to make. Axon Hub also provides insight into your application structure, so you can use Axon Hub to see the components inside the application handling events or producing commands and things like that. It can manage the event processors. This is a feature coming up soon in the next version of the Hub. It's able to dynamically scale the number of processors. If it sees, for example, if you're doing a replay, you might want to have more threads, more processing power to catch up in handling events, as opposed to when you're up to date and you're basically waiting for events to occur. So Axon Hub can manage that dynamic scaling between multiple instances as well. And Axon Hub is aware of bounded contexts. So we have this concept of a context in Axon Hub. So you publish an event in a context, and application listen to events in a context. So you can be very conscious about what information you want to share where. And the way Axon Hub is able to do that is, if you look at how smart systems are, and this is not a quality predicate, right? Systems can be dumb but really valuable, and they can be smart but not, or vice versa. But this is about how much they know about the contents of the messages that they are transporting. And if you look at the right end of the spectrum, you'll see the ESB, the Enterprise Service Bus there. They understand the content of messages. They can do transformations. They can do routing based on specific content. And you'll find that they are quite hard to configure and maintain. And in a lot of companies, you'll see a department that manages the service bus. And if you want to connect to it, you need to have you need to get in touch with that department and ask them to add you to that bus. On the other opposite, we have the typical message brokers. And they send messages. They don't really add routing capabilities other than pub/sub, right? They don't understand the contents of a message and just publish it anywhere where components are being or have been registered. And Axon Hub sits somewhere in the middle, a little bit more to the left and to the right. So we don't understand the contents of a message, but we do understand the type of the message. So we know a message is a command, is an event, or a query, and we know how to route those commands slightly differently based on their stereotype. We don't care about the payload or the content. That is really up to the application, right? So Axon Hub does not do transformation of messages. So if you want to consume a message from one context, transform it and publish it to another context, you probably have a component that does that on your behalf. It will ask Hub to send it all the messages of a specific type, and it will send other messages to another context in Axon Hub. So in the UI, so Axon Hub does come with a UI, and in this screenshot we have our example application running, which you can find on our GitHub. It's the gift card demo application. You can download Axon Hub from the website. You can start the gift card application, and if you start the different components, you can see here I've started 2 gift card command components. I've started 1 instance of the GUI and 1 instance of the query, and they are connected to Hub, which is connected to an Axon DB instance. all on the same machine. Now, if you click on one of those nodes, in this case, I've clicked on GC query, you can see some information, not very interesting in this idle example because all values are 0, but you can see that there's one instance running of this this service, and that it accepts 2 types of queries. We can see the queries that it accepts, and you can also see it has a tracking processor active at the moment, right in the bottom of the screen, and we can pause that processor if we want to, which is always interesting. Why would you want to do that? Well, maybe you want to balance the load to other nodes instead, so you can pause it on one machine so that another machine can take over processing for that thread, or for that segment. So the other product that that I've been talking about is AxonDB, and AxonDB is responsible for the storage of the events. It's really optimized for event sourcing, and it takes into account that event streams are append only and virtually unbounded. And the design of AxonDB is such that the performance will not decrease, unlike unfortunately the relational databases that we could use as an alternative. It doesn't decrease over time. So the performance of AxonDB is independent of the amount of data that it stores. And we were able to do that because we can make certain assumptions about the access patterns of the events, because it's optimized for event sourcing. And typically what you see is that events that have been recently added are much more frequently accessed than the events that have been sitting in the database for a longer period of time. So we optimized for that access pattern. And AxonDB comes with a UI as well, and that UI allows you to execute queries. So you can query that database, and in this example, again running against the gift card application, I'm querying for all events of a certain payload type that happened in the last hour. And this is these queries are real time. So as events are added, of course they're added in the last hour because it's real time. You can see those events being added to the UI at real time, and that also works when you do group by style queries. So you can do aggregations, doing counts on things, and they are updated at real time as events are added to the event store. So basically, this is our story of how Axon Framework, together with Axon Hub and DB, provide you with this way of evolving yourself into event-driven microservices instead of a big ball of mud.